Chapter 17, Second Order Differential Equations, Section 17.1, Second Order Linear Equations. A second order linear differential equation has the form p of x times the second derivative of y with respect to x plus q of x times the first derivative of y with respect to x plus r of x times y equals g of x, where p, q, r, and g are continuous functions. When g of x is equal to 0 for all x, in the equation in the previous definition, it is called a homogeneous linear equation. Thus, the form of a second order linear homogeneous differential equation has just the entire thing equal to 0. So if g of x is not equal to 0 from some x, then the equation is non-homogeneous. If y1 of x and y2 of x are both solutions of the linear homogeneous equation, and c1 and c2 are any constants, then the linear combination y of x equals c1 times y1 of x plus c2 times y2 of x is also a solution. So what we're saying is we have two solutions that we can plug in for y, and they'll make this thing equal to 0. In that case, then we can take those two equations, we can scale them by some scalars c1 and c2, and then that'll also be able to be plugged in to get 0. So let's prove that real quick. Since y1 and y2 are solutions of our linear homogeneous equation by assumption, that means that we have 0 when we plug them in. This is just the second derivative. It's just the same thing but difference in notation. I'm using prime instead of Leibniz. So using the basic rules for differentiation, we can see that if we plug in y, then what we'll do is we'll replace y with what we said we want y to equal, c1 times y1 plus c2 times y2. So we do that everywhere. And then we take our second derivative of a sum. It's just a sum of the derivatives, so these both become y double prime because we can take out the constant. Same thing over here. So then what we can do is multiply through by p of x, distribute, do the same thing for q of x, do the same thing for r of x, and then group together all of the terms that have c1 and factor out c1, and this is what you'll have left. And then group together all the terms that have c2 and factor that out, and this is what you'll have left over there. But we said that this thing was 0, so this thing is 0, and we said that this thing is 0 when we plug in y2, so that means this thing is 0. So that means that our entire thing is equal to 0, so that means that y, as we defined it, equal to this thing, makes our linear homogeneous equation equal to 0, so it is a solution. Okay, solutions y1 and y2 to a linear homogeneous equation are linearly independent if neither y1 nor y2 is a constant multiple of the other. Otherwise, they are linearly dependent. So this next theorem is the one that will allow us to actually solve these things. If y1 and y2 are linearly independent solutions of a linear homogeneous equation on an interval, and p of x is never 0, then the general solution is given by that y of x we just talked about, where c1 and c2 are arbitrary constants. So this might look like the same theorem we just did, but there's a very subtle difference, namely that we said that this thing would be a solution, whereas over here for this theorem, we're saying that every single solution will look like this in some form. So this is only true though if we have y1 and y2 as linearly independent solutions. So that's pretty cool because that means that if we find any two linearly independent solutions of a linear homogeneous equation, then we get every single possible solution using this theorem. This theorem is actually kind of tricky to prove, so we're not going to prove it, but we will use it. So we'll try to figure out solutions to some linear homogeneous equations. It's very hard to actually do that in general. So instead of making p of x our coefficient times y double prime, and q of x our coefficient times y prime, and r, we'll instead use constant values for p, q, and r. So we'll make those constant a, b, and c, because when they're constant, it's actually much easier to solve homogeneous linear equations. So what we'll do is we'll find some function that we can differentiate a bunch of times and plug in, and a great candidate for that is e to the r times x, because the derivative is r e to the r times x, and the second derivative is r squared e to the r times x. So that means that it'll be a solution to this linear homogeneous equation with constant coefficients as long as we plug it in for y and get 0. So that's what we do over here. But because it's in each of the terms, we can factor it out. And the cool thing is that it's never equal to 0, because e to the rx is never equal to 0. So that means that it must be a solution provided that this quadratic equation is equal to 0. So it's a quadratic equation, so it has two roots. So if we can figure out what the roots of that equation are, then we can figure out what our solutions to our homogeneous linear equation is. So because this quadratic equation is so special, it's got a special name called the auxiliary equation or characteristic equation. And its roots can be found by factoring or using the quadratic formula. So because we have a quadratic equation, and we're using the roots to determine what the solutions to our linear homogeneous equations are, that means that we've got three possibilities. Either we've got two real roots, or we've got one real root, or we've got two complex roots. So how about we deal with the first case? If b squared minus 4ac is positive, the discriminant is positive, then our roots r1 and r2 of the auxiliary equation are real and unequal. So that means that our general solution will be given by y equals c1 e to the r1x plus c2 e to the r2x. Let's prove that real quick. In this case, the roots r1 and r2 of the auxiliary equation are real and distinct. So one solution would be e to the r1 of x, because remember, we're saying that e to the rx is a solution provided that this thing is equal to 0, which will happen when r1 is a root. But it'll also happen when r2 is a root. So that means that y1 and y2 are both solutions. So by this theorem that we have, because they are linearly independent, they're not scalar multiples of each other, and that means that those two combined give us every single possible solution to our linear homogeneous equation. So we just plug them in for y1 and y2, and that's all there is to it. So let's do an example of this real quick. How about we try to solve this linear homogeneous equation? Notice that the coefficient over here is 1, this one's 1, this one's minus 6, so those are all constants. So we're able to solve this by taking a look at the auxiliary equation. So our auxiliary equation is r squared plus r minus 6. We just take the coefficients, and this means that we can factor it as r minus 2 and r plus 3. I want to see where that's equal to 0. So that'll be equal to 0 when r is equal to 2 and when r is equal to minus 3. So we can see that we got two distinct roots. How about we set r1 equal to 2 and r2 equal to minus 3, and then we can just plug in to our solution equation, y equals c1 times y1, so that'll be e to the r1x, so that's e to the 2x, plus c2 times y2, and that'll be e to the minus 3x. Okay, let's do that again. We could solve this differential equation. This thing is just y double prime, this thing is y prime, and that's y. So reading off our coefficients, we have 3r squared plus r minus 1 equals 0 for our auxiliary equation. So we'll do the quadratic formula, and we get r is equal to minus 1 plus or minus the square root of 13 over 6. So that means that y equals c1 times e to the minus 1 plus the square root of 13 times x over 6 plus c2 times minus 1 minus the square root of 13 times x over 6 is a general solution to this differential equation. How about we do our second case now, where we could have one real root. So if we have one real root, that means our discriminant is equal to 0. Then we end up with this formula for the general solution. So notice it's slightly different, even though r is in both of these guys now, because there's only one r, we've thrown an x in there. So let's show that this is actually the solution. By the quadratic formula, we can solve our auxiliary equation to get that r is equal to negative b over 2a. So that means that 2r plus b is equal to 0. We know that e to the rx is already a solution to this linear homogeneous equation. So we just need to check that this is also a solution. And then once we know that they're both solutions, we use our theorem, we plug them into y1 and y2, and we have our general solution. So to check that it's a solution, we just pull up our linear homogeneous equation, we plug in 2r e to the rx and r squared x e to the rx, because that's what the second derivative of y2 is. Then we take the first derivative of y2, and we have to use the product rule, and we get that, so we plug that in times b, and then we plug in for y times c. So what we can do is distribute our a, factor out e to the rx, distribute over here our b, and factor out x e to the rx from everything, and we'll end up with 2ar plus b and this thing times x e to the rx. But we said that 2ar plus b is equal to 0 because r is equal to minus b over 2a, and this thing is equal to 0. So that means that this is equal to 0 and this is equal to 0, so our entire thing is equal to 0. So that means that x e to the rx actually is a solution, and because now we have our y1 and y2 solutions, they're linearly independent. Now we know every single possible solution, and it's going to be of this form. So let's solve another differential equation, but this time we will be careful to throw in an x because we're going to have one root. So just to verify that, our auxiliary equation is 4r squared plus 12r plus 9 equals 0. By reading off our coefficients, we have 2r plus 3 squared equals 0 by factoring, and that means that r is equal to minus 3 over 2, and there's only one of them, one distinct one. So that means that it must be, our solution must be the form y equals c1 times y1, which is e to the minus 3x over 2, plus c2 times x times e to the minus 3x over 2. For our last case, we have the discriminant negative. In that case, we have a negative inside of the square root in the quadratic formula, so our roots are complex. And in that case, we end up with roots as, let's say, alpha plus I beta and alpha minus I beta, because they have to be conjugate roots. So that means that our general solution will be given of this form. So to prove this, we need to use Euler's equation, which of course we won't prove. So we'll write the solution of the differential equation as c1 times e to the r1x, c2 times e to the r2x, except that our roots are now complex, so we throw those complex roots in for r1 and r2. Next, we'll use Euler's equation so that we can write the e to the I beta x part as cosine beta x plus I sine beta x, and we'll leave e to the alpha x separated. And then we'll do the same thing over here. We'll do e to the minus I beta x as cosine beta x minus I sine beta x, and leave e to the alpha x separated. Then we can factor out e to the alpha x, and we'll have c1 plus c2 times cosine beta x, and I times c1 minus c2 times sine of beta x. So that's the same thing as just some constant. We can take c1 and c2, it's arbitrary, so it's just as arbitrary as c1, we just relabel it. And then we do the same thing with c1 minus c2, we just relabel that some other second constant, as long as we throw that I in there. Okay, so that means that we can solve this linear homogeneous differential equation now. Our auxiliary equation is r squared minus 6r plus 13 equals 0. So that means that our roots using the quadratic formula are 6 plus or minus the square root of 36 minus 52 over 2, which is 6 plus or minus the square root of negative 16 over 2, which simplifies to 3 plus or minus 2i. So that means that we have y equal to e to the 3x, because that's our alpha, times c1 times cosine of beta x, so that's 2, plus c2 times sine of beta x, so that's 2x again. An initial value problem for a second-order linear differential equation consists of finding a solution y of the differential equation that also satisfies initial conditions of the form y of x naught equals y naught and y prime of x naught equals y1. Notice that we need to know both the initial value of y and the initial value of the derivative of y in order to be able to solve for this thing uniquely, because we have y double prime in addition to just having the derivative. So this is similar to our initial problem for first order differential equations. It's also similar to the way that we would do anti-differentiation. If we did an indefinite integral, we would have some constant c, but if we knew an initial value, then we could solve for that constant c and we could have a unique solution. So because we know some initial values over here, we can plug those in so we won't have any c's in the end. We'll know exactly what those c's are. So for this problem, how about we let y of x equal our solution, c1 times e to the 2x plus c2 times e to the minus 3x. Remember, we just pulled this from example 1 where we just solved the same differential equation. So now let's plug in for c1 and c2. We'll have to figure out what those are. We'll take our derivative, y prime of x, and we'll get that that's 2 times c1 e to the 2x minus 3 times c2 e to the minus 3x. And then we're given that y of 0 is 1. So that we'll plug that in for y. We'll see that y of 0 is, well, this thing becomes 1 and this thing becomes 1. So we just have c1 plus c2. And that must be equal to 1. So how about y prime? We know that y prime of 0 must be 0, so that means that 2 times c1 minus 3 times c2 must be equal to 0 by our second equation. So now we can solve for c2, and by isolating it we see that c2 is 2/3 times c1. So how about we plug that into over here for c2. So then this equation over here will tell us that c1 plus 2/3 times c1 must be equal to 1. So now we can solve for c1. We see that c1 is just 3/5. So plugging that back into c1, we see that c2 is equal to 2/5. So that means that our solution to this initial value problem is y equals 3/5 e to the 2x plus 2/5 e to the minus 3x. Let's solve this initial value problem now. So we haven't seen this differential equation before, so we need our auxiliary equation. So that's r squared plus 1 equals 0 in this case, by just reading off our coefficients, because we don't have any r's because we don't have any y primes. So solving for r, we get that r squared is equal to minus 1, which means that r is equal to plus or minus I. Okay, so that means that we need to plug into our solution for a complex case. So notice this is 0 plus or minus 1i, so alpha is equal to 0. and beta is equal to 1. So e to the alpha x is e to the 0x, which is just 1. So our solution is given by y of x is equal to c1 times cosine 1x plus c2 times sine of 1x. So that means that y prime of x is equal to minus c1 sine x plus c2 times cosine x. And we know that y of 0 is equal to 2, so we plug in 0 over here, and this term disappears. Sine of 0 is 0, cosine 0 is 1, so we just have 1 times c1, so that must be 2. So now we know what c1 is. Similarly, y prime of 0 we're told is 3, so we plug in 0, this is eliminated, and then we just have 1, so 1 times c2 equals 3. And now we know what c1 and c2 are, so we have our solution given as y of x equal to 2 cosine x plus 3 sine x. A boundary value problem for a second-order linear differential equation consists of finding a solution y of the differential equation that also satisfies boundary conditions of this form. So notice in this case, we don't have an initial value for y prime. Instead, we're given 2 values of y. So these boundary value problems do not always have solutions. They're a little bit trickier. So how about we take a look at this one? We'll first solve our differential equation. So we'll look at our auxiliary equation, which is r squared plus 2r plus 1 equals 0. So we can factor and see that we get r plus 1 squared is equal to 0. So that means that r is equal to minus 1. So there's only one unique root. So that means that y of x must be given by c1 times e to that root minus 1 times x plus c2 times x times e to the minus x. So we have y of 0 equal to 1. So plugging in 0 over here, this is eliminated because of the extra x in there. So we just have c1 times 1, so c1 must be equal to 1. So if we plug in y of 1, then we get c1 times e to the minus 1 plus c2 times e to the minus 1. And that must be equal to 3 by this criteria over here. So what we can do is we can plug in the value of c1 that we determined. So we'll get e to the minus 1 plus c2 times e to the minus 1 must be 3. And we can just multiply through by e. We get 1 plus c2 is equal to 3 times e. So that means that c2 must be equal to 3e minus 1. So our solution is given by y equals e to the minus x plus 3e minus 1 times x e to the minus x.